Thermocouple is a long word. So to save space on my slides, I use the abbreviation T/C. Remember that one. A thermocouple consists of two wires of dissimilar metals joined at the heated end, or junction as it's called, and connected to circuitry on the other end. The voltage read at the heated junction is proportional to the temperature at that end and the choice of the two metals. A guy named Thomas Seebeck discovered this phenomenon back in 1821, and of course it got named after him. We call it the Seebeck effect. And you thought we named constants or laws of physics only after 19th century guys named Ohm, Volta, Ampere, Kirchhoff, and Coulomb. Nope, this one's named after Thomas Seebeck. Bare thermocouple wires range in diameter from 0.1 to 3 millimeters. The smaller ones are very fragile, but they'll give you a fast response time when heated. Unless you need response times well under 1 second, you will want to buy a thermocouple protected inside a metal sheath, possibly with ceramic insulation between the wires. Otherwise, it won't last very long when you use it to measure temperatures over 1,000 degrees C. And now it's time for thermocouple fun facts. The measurable temperature range varies greatly by which alloy pairs you pick. One pair of obscure alloys known as a Type C thermocouple will accurately measure temperature up to 2,300 degrees Celsius as long as you use a titanium sheath to protect it. The United States National Institute of Standards, which we call NIST for short, publishes a ghoulishly long standard called ITS-90. It lists the thermoelectric voltage for every pair of thermocouple alloys at intervals of 1 degree C. You can download it for free and use it to create table lookup software for measuring temperature with thermocouples. Alloy pairs are given letters of the English alphabet, types J, K, T, and so on. I have no clue why those letters were used, as they don't correlate to the names of the alloys or the metals inside them. Type K is the most popular one in use because of its broad temperature range and its low cost. Typical accuracy is 1% of reading. To do better than this, you'd have to ask your supplier to individually calibrate each thermocouple probe they sell you. Here's a slide summarizing the thermocouple alloy pairs. Some of the materials are pure metals like iron and copper. Most are obscure alloys with names like chromel and constantan. Only a few companies in the world make these alloys, which of course is why I call them obscure. Types K and T allow you to measure very cold temperatures found on the outer planets. Type C is good for jet engines. And the nominal voltage sensitivity is just that. It's nominal. You need to get the actual thermoelectric voltages off the ITS-90 table. Here's some thermocouple voltage curves for types J, K, and S. Thermoelectric voltage versus temperature curves are nonlinear, and you get small negative readings at the very cold temperatures. You can assume linearity for small changes in temperature by using the slope B of the nonlinear curve at the local temperatures. And if you do this, though, make sure you do your calculations in degrees K, or you're gonna get into trouble with signs for temperatures below 0 degrees C. Here's an excerpt from the table ITS-90, the thermoelectric voltage table. In this case, it shows type T voltage data. You read the temperature on the left column in 10 degrees C intervals, then you read across the top row to find your reading to the nearest 1 degree. You intersect the row and the column, and you find the thermoelectric reading in millivolts. For example, to find the thermoelectric voltage for 364 degrees C, you first find the row corresponding to 360 degrees C, and then the column corresponding to 4 degrees C. And at the intersection of those rows and columns, you read 18.665 millivolts for the thermoelectric voltage. Thermocouples get used mostly for low-cost contact temperature measurements above 800 degrees C. And as such, you find heavy usage in the aerospace, the heat treating, and the metal forming industries where people have no choice but to use thermocouples. Sometimes people use them for their lower cost than RTDs, as long as they don't mind recalibrating or replacing the thermocouples annually. Some applications like automotive or aerospace engine test stands require hundreds of measurement points, and then cost competitiveness of the temperature sensor becomes a bigger factor in a user's decision-making of which temperature sensor to use. Injection molding machines are a popular application for thermocouples. They're used to monitor the melt temperature of the plastic as it's injected into the mold cavities. The temperature shows up as a control signal on the monitor of this molding machine. I showed you what commercial RTDs look like, so of course, I have to show you what thermocouple probes look like. You can buy them as a straight probe with a connector on the end, like this one on the left from Automation Direct. The penetration probe in the middle of the slide from ThermoWorks is commonly used to measure the temperature of cooked meat in a commercial kitchen. The flexible cable on the end gives the cook more flexibility to move around when using it. The probe on the right from Pyromation is designed to screw into a threaded hole in a furnace. The loose wires on the right would extend outside the furnace to be screwed into a thermocouple connector. Let's recap. We discussed the accuracy, the range, and the applications for thermocouples. Now we're going to use more circuit diagrams to explain the principle of cold junction compensation and a bit about how to purchase thermocouples.